All right, this video is going to go over pages 17 through 19. So we're going to do some more calculation practice on this one. So this page is purely relationship stuff. So there's not really calculations. It's if you increase one, how it will affect the other. So remember, we talked about in the last video is if acceleration goes up, force goes up as well. And that was the direct relationship. If mass goes up, acceleration has to go down, which is an indirect relationship. So these are what you need to know in order to answer this page. So 5, suppose that a sled is accelerating at a rate of 2 meters per second squared. If the mass is doubled, then what is the new acceleration of the sled? So if mass goes up by 2, okay, I want to know what happens to my acceleration. Well, if I go back up here to the top, we know if mass goes up, acceleration does the opposite. It goes down. So if the opposite of multiplying by 2 would be dividing by 2. Okay, so I'm going to take that acceleration that I had, which was 2, so 2 divided by 2, and now I have a new acceleration of 1 meters per second squared. 6, suppose that a sled is accelerating at a rate of 2 meters per second squared, so it's the same sled every single time. If the net force is tripled, so F net is tripled, so it goes up by 3. What is my new acceleration? So remember, if we go up here, if force goes up, acceleration goes up. So that means it's going to do the exact same thing. So acceleration will triple as well. So 2 times 3 is going to give me 6 meters per second squared. Number 7, suppose that a sled is being pushed with a net force of 2 newtons. Okay, so I have a force. If the acceleration is doubled, what is the required net force needed in order to accelerate the sled at this rate? So if my acceleration is doubled, so A goes up by 2, remember A and F go hand in hand. That means force is going to go up as well by 2. So I'm going to take that 2, multiply it by 2, and I get 4 newtons. Now number 8 and 9, this is where it can get tricky, but if you just take it one step at a time, it's not too bad. If you try to do it all at once, then it gets confusing. Okay, so we're going to take that sled again. If the net force is tripled and the mass is doubled, what's my new acceleration? So I'm going to start off with just the net force is tripled part. If force goes up by 3, I know acceleration has to go up by 3 as well. Okay, so I'm going to take that 2, so 2 times 3 gives me 6. So that's my new acceleration right now. Now I'm going to look at my mass. Okay, so if mass is doubled, so m goes up by 2. Remember, acceleration goes the opposite way, so a is going to go down, and we're going to divide by 2. So I'm going to take that 6 that I just found here, so I'm going to do 6 divided by 2, and my new acceleration is 3 meters per second squared. Number 9, suppose that a sled is, so same sled, if the net force is tripled, so let's just worry about that. If force goes up by 3, acceleration is going to go up as well by 3. Okay, so 2 times 3 gives me 6. Okay, now my mass is halved. Okay, so mass went down. It divided by 2. Okay, so that means acceleration is going to do the opposite. So A is going to go up by 2, so we're just going to double. So take that 6 we just found, so 6 times 2, and I get 12 meters per second squared. Okay, now flow chart is, we're just going to kind of recap Newton's first law and second law. So we're just going to draw a flow chart real quick. It's going to be pretty simple. So Newton's first law, we're going to kind of go back to that. So Newton's first law, if I could write. Okay, this is when everything is nice and balanced. Okay, now you got 2 scenarios here. You have your object that's at rest. Okay, so if you're at rest, that means your velocity is 0. Okay, which means your acceleration is 0 because you're not speeding up, you're just sitting there. And if acceleration is 0, that means your net force is 0 as well, so 0 newtons. So that would be considered balanced. It's not moving. Okay, if it was unbalanced, then it would be either accelerating or decelerating. Now, your other option is if you're not at rest, okay, and if everything needs to be balanced, that means you're moving at a constant velocity. Okay, so it has to be constant. So we know velocity is not equal to 0. But if you're going at a constant velocity, you're not accelerating either. So A would be 0 as well in this scenario. And if A is 0, then that means F net is 0 as well. Okay, so that was type 1, basically type 1 in a nutshell. Okay, so what we're going to do is we're going to do type 2. or not type 2, Newton's second law. Sorry, I went back to projectiles there for a second. So Newton's second law. This is when everything is unbalanced. That means we have a net force that's not equal to 0. So F net does not equal 0 newtons. So you either have something that's accelerating because of force. So remember, if A goes up, force goes up. Okay, and that was a direct relationship. Okay, or you have accelerating changing because of mass is changing. So if mass goes up, acceleration goes down. So that would be called indirect. Okay, so that's basically Newton's second law, is there is acceleration. It's either caused by a force that's unbalanced or it's caused by a mass that's unbalanced. Okay, so we're going to do some more calculation stuff. So now here is what we're going to do is we're actually going to incorporate F equals ma with Daffy T. Okay, so a 2 kilogram object originally at rest is pulled on a horizontal frictionless table by a constant force of 6 newtons. Okay, so what we're going to do is we're going to kind of break this sentence down as we're looking at things. So if you look at problems like this and you start kind of getting overwhelmed, okay, by this material, okay, one of the things you can do to make things easier on yourself is to start labeling things. That way you can at least figure out what you have. Okay, so that's what we're going to do is a 2 kilogram object. So there's your mass originally at rest. Okay, so that means your VI is going to be 0. Okay, so you got to watch out for terms like that. Okay, is pulled on a horizontal frictionless table by a constant force of 6 newtons. So there's your force. It says calculate the velocity. So if I already know VI is 0, that means we're looking for VF. And of the mass, it's 3 seconds after the force starts acting. So there's your time. Okay, so there's a lot going on here. Okay, so we are looking for VF. So I know VF is right here in the Daffy T. So what we're going to do is we're going to set up our Daffy T. Okay, so VF is what we're looking for. We know VI is 0. We know time is 3. I don't know A, and I don't know distance. And I don't know which one to put a line through, and I don't know which one to fill in. So this is what we mean by we can start incorporating F equals ma. If you look, A is the only thing that's interchangeable between these two. So if you don't have A on one of these, you can use the other one to find it and then bring it over. So I do have a force. I do have a mass. So over here, I'm going to find it. So 6 equals, so remember F equals ma. So 6 equals 2 times A. So divide both sides by 2, and you get an A of 3 meters per second squared. Now what I can do is I can bring that over here to my Daffy T, and that means I did not care about distance. So we're going to use equation number 1. Okay, that's where we drew our line through. So VF equals VI plus AT. So VF we don't know. VI is 0. A is 3. T is 3. Okay, so multiply those and you get a final velocity of 9 meters per second. Number 2, 1,000 kilogram car. There's my mass. Moving eastward, there's a direction, along a horizontal road at a constant speed of 12 meters per second. So I gave you velocity. I didn't tell you if it was VI or VF, so we'll figure out that in just a second. On A, it says, what net force acts on the car? Well, you got to look out for terms like this, constant speed. That means A equals 0. And if A equals 0, that means F net has to equal 0 as well. Now B, if the brakes are applied and the car is brought to a rest in 6 seconds, so brakes are applied, so it's brought to a stop. So that means VF is now 0, which makes that 12 up here VI. And I gave you time is 6 seconds. What constant net force acts on the car? So that means you're looking for force. Now, good thing is do not get constant speed and constant force mixed up. A lot of times students they just see that constant and they just assume F net's 0. Okay, that is only if you're at a constant velocity. Okay, we're just wanting to know what is the constant force you have to apply to bring that car to a stop. So we're looking for F. We know F equals ma. Okay, so F equals ma. So F equals our mass we know is 1,000. A we don't know. Okay, so what we're going to do is we're going to do Daffy T over here. So we're going to set up Daffy T, and we're going to find our A and bring it back over. So A is your question mark. Okay, VF is 0 because you're coming to a stop. VI is 12, and your time is 6. That means we did not care about distance. So we're going to use equation number 1 again. So that whole VF equals VI plus AT. So 0 equals 12 plus A times 6. Now what I'd do is I'd bring that 12 over. It becomes negative 12 equals 6A. Okay, divide both sides by 6, and you get acceleration of negative 2 meters per second squared. So it is okay to get negative because it's bringing you to a stop. Okay, so that is negative acceleration. So now what we can do is we can bring that over here to what we were trying to do in the first place. So A is now negative 2. So multiply those and you get negative 2,000 newtons. 3, what constant force is required? So you're looking for force. There's your question mark. It's required to move an object starting from rest. So that means VI equals 0. A distance of 75 meters, so there's D. Along a horizontal frictionless table in 5 seconds, there's T. And I gave you the mass. Okay, so I'm looking for force. So force equals mass times acceleration. So F equals my mass, which is 4. And I don't have my A again. So what we're going to do is we're going to set up our Daffy T to find it. Okay, so D, we don't know. Well, actually we do. In this one we know it's 75 meters. A is what we're looking for. Okay. VI, we said starting from rest, so VI is 0. Okay, and my time was 5. That means we did not care about final velocity here, so you're going to equation number 3, which is that D equals VIT plus 1/2 AT squared. So if VI is 0, this whole VIT goes away, so it's just D equals 1/2 AT squared. So 75 equals 1/2 A times 5 squared. Now what I would do is I would square 5, which is 25, okay, and then half that. So that's basically saying 75 equals 12.5 A. And then divide both sides by 12.5, and you get an acceleration of 6 meters per second squared. Now I can do is I can bring that over here to my F equals MA. So 4 times 6, and I get a force of 24 newtons. And that will end that one.